Assalamualaikum. My name is Amira Sofia binti Ikwan, student of Chemistry with Management AS222. I will be presenting to you about my study on behavior of 9,2,2-dicyanovinyl dualidine DCVJ in deep eutectic solvents DS and molecular solvents. In this presentation, I will be discussing on introduction, literature review, methodology, results and discussion, and conclusions. As a start, our surroundings are involved with solvents and solid. A solvent can take the form of a solid, liquid, or gas. Organic solvents and inorganic solvents are the two main types of solvents, which has been written by Hall 2020. Organic solvents are carbon-based solvents, for example, methane, ethanol, DES, and molecular solvents, whereas inorganic solvents have lack of carbon-carbon bond or carbon-hydrogen bond, for example, silver, carbon dioxide, and salt. In this study, I will use DES and molecular solvents. Molecular solvents has been used widely in environment in biochemistry industry and pharmaceutical industry, and it is consists of one compound. Meanwhile, DES is a solvent with missing compound of HPA hydrogen bond acceptor and HPD hydrogen bond donor. These two solvents have different properties. Molecular solvents are volatile, hazardous, and not sustainable molecules, but the solvent has low viscosity. However, the green technology used now is deep eutectic solvents, which consist of two or more compounds, HPA and HPD, harmless, affordable, and sustainable molecules. However, these solvents has high value in viscosity. My objectives for this study is to prepare a series of deep eutectic solvents with different viscosity, to characterize the physical and chemical properties of DES using FTIR-ATR and 1-hydrogen NMR, and lastly, to find the correlation between fluorescence signals of DCVJ with the viscosities of DES and molecular solvents by plotting log intensity and against log viscosity and compare it with Foster-Hoffman equation. A molecular rotor can be described as a condition of fluorescent molecule that is able to undergo an intermolecular twisting motion at its excited state. Generally, it comprises three subunits: an electron donor unit, an electron acceptor unit, and an electron which has rich spacer unit, and made up of a network of alternative single and double bonds. This network of couples which are acceptor and donor units can move between them. By looking at this DCVJ structure, we can say that cyanide is electron accepting group, dualidine will act as electron donating group, meanwhile benzene and C1C here will act as electron rich spacer unit. DCVJ's fascinating fluorescent features are based on its capacity to lose excited state energy via radiation or intramolecular rotation, the ratio of which varies on the free volume of the microenvironment, which has been stated by Heidegger in 2001. DCVJ also has been used widely to solve some issues, including polymerization process, tubular remodeling, and membrane viscosity measurements in liposomes and the cells. This has been written by Heidegger in 2001. For example, when there is a diagnosis of cancer, DCVJ will be used as a probe to identify the viscosity of the cells in our blood. Next, use Foster-Hoffman equation to analyze viscosity in both polar and non-polar solvent, which has been done by Heidegger and Theodorakis in 2010. To prepare DES solvents, each solvents were prepared by according to their molar ratio by using direct mixing method. The mixtures were ground together using mortar and pestle, The mixtures were stirred using magnetic stirrer and heated at 50 degrees C for 2 hours or until colorless liquid obtained. The mixture is then dried in vacuum oven at 50 C to 63 degrees Celsius with pressure of negative 10 psi and operated at 8 hours. After that, the mixtures are allowed to cool down and kept in desiccator. This is how I set up my FTIR spectroscopy in 1 hydrogen NMR spectroscopy. For liquid solvents, the method used is FTIR ATR, attenuated total reflectance, by putting 1 drop of solvent into the sample holder and run FTIR spectroscopy at the scan wavelength 650 cm/cm to 4000 per centimeter and the scan resolution of 8 cm. For 1 hydrogen NMR, the DES samples were dissolved in deuterium oxide D2O and has been done 16 scans for 1 hydrogen at 50 MHz. And this is how I set up my UV visible spectroscopy and fluorescence spectroscopy. These are the results of CHCl urea and CHCl ethylene glycol. By comparing HPA-HPD and the mixture of HPA-HPD in IR spectra, we can see that the structure can be analyzed to show the synthesis are successful. Similar goes with the next one. In this figure shows FTIR spectra of CCl malonic acid and CCl glycerol. This also shows that the synthesis is successful. This is the result of the NMR spectra, which were analyzed by using Masranova 14 software and been used as additional information in analyzing the chemical structure of DES. This is 1 hydrogen NMR spectra of CHCl malonic acid and CHCl glycerol. UV spectra of DCVJ in polar molecular solvent has been analyzed using lambda max absorption with viscosity of solvents and dielectric constants, which is act as polarity of solvents. To conclude this figure, as the viscosity of solvents increases, the maximum absorption also increases and shifted to the right. Meanwhile, there is no trend in polarity. This is performing UV spectra of DCVJ in non-polar molecular solvent. The solvents used, which is hexane, dichloromethane, and toluene, have small gap in viscosity. Therefore, the lambda max absorption is at the same range. This figure shows fluorescence of DCVJ in polar molecular solvents and non-polar molecular solvents. In polar molecular solvents, we can see that there are different emission intensity along with lambda max emissions, as the solvents have wide range of polarity, whereas in non-polar molecular solvents, the emission intensity and lambda max emission is in small value and shows the intensity at a low value compared to polar molecular solvents. By plotting linear graph of log intensity and log viscosity, the graph is not perfectly linear, and due to small gap of viscosity of toluene, dichloromethane, DCM, and hexane, these solvents were scattered at range of -0.5. Next is UV spectra of DCVJ in deep eutectic solvents. In these figures, I can come to a conclusion whereby as the viscosity increases, the range of lambda max absorption also increases. Okay, next is fluorescence spectra of DCVJ in DS. We can see that from the table, as the viscosity decreases, the lambda emission max has shifted to the left. And by plotting graph linear of log intensity against log viscosity, it shows that the graph is almost linear but not perfectly. I can come to a conclusion whereby my probe, DCVJ, might have the same polarity with DES, which correspond towards the linearity of DES. In conclusions, deep eutectic solvents were prepared accordingly to its molar ratio with different viscosities, and physical-chemical properties of DES can be characterized by using UV spectra and 1-hydrogen NMR. And I also can conclude that DCVJ has similar range of polarity with DES by comparing R squared in molecular solvent, which is 0.6287, which is smaller compared to R squared in DES, which is 0.8378. Therefore, this shows that DCVJ reacts towards the viscosity of surrounding and does not correspond towards polarity of solvents. In recommendations, I would like to recommend for measure water content of the mixtures because due to the presence of water content, the mixtures may not viscous as it need to be. Next is measure polarity of DES quantitatively as it may help for this study since its intensity can be affected by two conditions which are polarity and viscosity. Third is use different type of dye that may have different sensitivity for further understandings. This is the references that I use for this study. Thank you so much for listening and thank you for your time to evaluate my presentation. That's all from me. Thank you.